Chapter 13. Internal and External Logic. There are exactly 4 kinds of numbers that can be added, subtracted, multiplied, and divided. In other words, there are exactly 4 division algebras: real numbers, complex numbers, quaternions, and octonions. The real numbers are one-dimensional. Pairs of real numbers make the complex numbers, which are two-dimensional. Likewise, pairs of complex numbers make the quaternions, which are 4-dimensional, and pairs of quaternions make the octonions, which are 8-dimensional. And that's the end of the line. That is, the octonions represent the last of the division algebras. No higher order pairings will allow all those symmetric operations. These division algebras reflect the closed division balances of the minimal arena's different constructive domains. The internal domain closes under 8-dimensional octonion connection, whereas the external domain rearranges those same parts to close under 4-dimensional quaternion connection, which defines a union of complex planes intersecting on the real line. Cayley logic table for the octonions portraying the 7 basis vectors and their algebraic connections looks like this. Since the octonion logic symmetrically connects 8 things, 7 basis vectors plus the external unitary projection, or the 1, under closed 3-member operations, it topologically decomposes into 8 simply connected triangles, or 2 tetrahedra. Recall that the hyperbolic figure 8 knot decomposes into a union of 2 regular ideal hyperbolic tetrahedra, and a tetrahedron decomposes into 4 simply connected triangles. To visualize the 8 symmetric triple groupings of the minimal arena's internal octonion connection, we graph the product of the interaction of balance 0 and balance 1. Both the real and complex graphs identify 2 inner groups of 3 and 2 outer groups of 3 that connect under 5-part asymmetric balance, defining the 8 3-member simply connected closed operations of the octonion logic. The minimal arena is internally bound into the hyperbolic figure 8 knot under octonion connective logic, and externally bound into the n-hypersphere of maximal volume under quaternion connective logic. This quaternion connection is supersymmetrically coded by the fact that every possible labeling, A, B, C, D, of the real and imaginary parts of the 3rd and 4th hyperbolic vortex partition constants satisfies the quaternion algebraic identity. The square of AC minus BD plus the square of AD plus BC is equal to the product of A squared plus B squared and C squared plus D squared. Paired labelings, those that group real and imaginary parts together, constructively define the hyperbolic vortex radius to the 4th power. That is, if we restrict the way we label our parts and make sure that we have parts that are real and imaginary put together, then this construction isn't just mapping the algebraic identity of the quaternions, but it's also characterizing the limit of the hyperbolic vortex radius to the 4th power. Another baked-in consequence of the minimal arena's external shape is calculus. In addition to the fact that the generalized power series of the external domain's hyperbolic connection, so e to the x, defines the elementary derivative sequence, where every term in this series defines the derivative of the following term, the derivative geometrically defines how the volume of an n-dimensional hypercube increases or decreases as the side length of that hypercube is changed. On the other hand, integrating this picture, or stacking the faces, geometricizes the fundamental theorem of calculus, yielding a decomposition of the n-cube into n-pyramids, which is a geometric proof of Cavalieri's quadrature formula. What the minimal arena's external projection looks like depends on the scale we focus on. On its grandest scale, which is very specifically 1.416786985900795 times 10 to the 32 meters, the n-hypersphere of maximal volume defines the simplest possible geometric form in S3, the great sphere, minus its boundary. On its smallest scales, between 1.8755546713962 times 10 to the negative 18 meters and 2.1764268 on times 10 to the negative 8 meters, It defines the second simplest geometric form, the minimal hypersurface known as the Clifford Taurus. Here we are diagramming the projective tangent cone of the Clifford Taurus, the familiar conic division boundary of projective hyperbolic geometry. The tangent cone of the Clifford Taurus defines the projective null cone of hyperbolic geometry. The entire surface of this hypercone defines the division singularity of the external domain, and the balance maintained by this constructive arrangement between the future hypercone and the past hypercone defines the hyperplane of the present, the most trivial minimal hypersurface. As a helicoidal product surface, the Clifford Taurus defines the simplest and most symmetric flat embedding of a Cartesian product of two circles. That is, it defines the simplest connection between two circles, each of which possess their own independent embedding space, resulting in a product space that's R4, the four-dimensional hyperbolic spacetime of general relativity. But that's not the end of the story. Since this helicoidal surface connects two circles of significantly different size, the chiral connection of its rotation operator is highly asymmetric, causing the Cartesian product of these two circles to twist into an R3 torus. Under asymmetric chiral connection, this is unavoidable. The first circle in that connection consumes x and y, leaving only one independent axis, z, available to the second circle. This quickly collapses the R4 domain into an R3 projection. That is, a torus embedded in R3 is an asymmetric reduced dimension projection of the maximally symmetric Clifford Taurus embedded in R4. The generalized equation for the tangent cone of the Clifford Taurus is the four-dimensional relation x1 times x2 is equal to x3 times x4, where x sub k is the kth factor or dimension of its connection. The null cone of the n hypersphere of maximal volume is set by the four rotations of the minimal arena's terminal division boundaries. Rotation of the length boundary times by the rotation of the mass boundary equals the rotation of the charge boundary times by itself, or the charge rotation squared. This null cone defines the Clifford Taurus with maximum square symmetry. That is, for any possible set of different sized circles put into Clifford Taurus arrangement, the product of the left pair of operators equals the product of its right pair of operators. But for one supersymmetric Clifford Taurus, there exists an additional square symmetry, where one of its paired sets of operators also share an equality between them. The null cone of this maximally square symmetric Clifford Taurus defines the projective division boundary of the n hypersphere of maximal volume. The other minimal hypersurfaces embedded in this geometry, those that play a role in the helicoidal collapse from R4 to R3, are found by generalizing the Clifford Taurus via the method of separation of variables. These are all the minimal hypersurfaces that can be obtained by the method of separation of variables. J. Young Chow.